Carlos Plain, an instructor at Durham School, states that his entire career has been dedicated to empowering a particular theory about the universe. Over time, as new discoveries unfold, this theory is continually examined. He embraces this process of scrutiny, as it is through such investigations that progress is made in the realm of science. The James Webb Space Telescope, JWST, has made groundbreaking revelations that challenge long-standing beliefs in cosmology, beliefs that were once considered absolute truths for over a century. Recent images captured by this telescope have unveiled that previous assumptions in space science were flawed. Originally designed to observe the formation of the earliest stars in the universe, the telescope has presented challenges to existing ideas, suggesting that our previous perspectives may require a fundamental revision. However, not all experts are dismayed by these new findings. Many are welcoming these changes, as it has long been evident that there were inconsistencies in past theories. Issues with how the universe's rate of expansion was measured should have raised concerns among specialists much earlier, but instead of addressing these warnings, many persisted with outdated models. The cosmic microwave background, CMB, radiation, which is the oldest light in the universe, was created about 380,000 years after the Big Bang. During this time, the universe cooled sufficiently for electrons and protons to bond into stable hydrogen atoms, a process known as reionization, which made the universe transparent to light. In 1964, American physicists Arnold Penzias and Robert Wilson detected this radiation while working with a new radio receiver. They initially thought it was just background noise, but their discovery later became pivotal evidence for the Big Bang theory. Their work earned them the Nobel Prize, and their findings became a cornerstone in the history of space science. The CMB provides a glimpse into the early universe, with subtle temperature fluctuations that offer valuable information about the conditions shortly after the Big Bang. Researchers have used the CMB as a reliable marker to measure significant aspects of the material universe, including the rate of its expansion. Edwin Hubble, in the late 1920s, had already calculated that distant galaxies were moving away from us in all directions, with their speed correlating to their distance, a relationship now known as the Hubble law or Hubble constant. Though Hubble's estimates weren't as precise as current measurements, they were still groundbreaking. When the CMB was discovered, scientists recalculated the universe's expansion rate, finding it to be significantly lower than Hubble's original estimate. Further recalculations using Type Ia supernovae as standard candles offered more accurate measurements, but discrepancies still persisted. These differences in expansion rate calculations have been recognized since the 1990s, with scientists speculating that issues might exist in CMB data analysis methods or in our understanding of cosmic expansion. This inconsistency, referred to as the S8 tension or Hubble tension, suggests that our interpretation of the universe might be fundamentally flawed. Since the JWST began its observations, it has provided exceptional data that could help explain this dilemma. Some of the galaxies it has observed are so ancient that their formation may have begun even before the Big Bang, presenting a serious challenge to established scientific theories. Cosmology now faces what could be considered its greatest crisis. The rate at which the universe is expanding and how we conceptualize its origins are under intense scrutiny. New images have revealed a universe that starkly contrasts with past models, and the S8 tension serves as an early warning for scientists still clinging to outdated theories. The recognition that our understanding of the cosmos may be incomplete has left many researchers frustrated and perplexed. To address this crisis, it's essential to understand the nature of scientific inquiry. Theoretical scientists use a combination of mathematical models, observational data, and logical reasoning to arrive at conclusions. Their knowledge comes from observing anomalies, testing results, and engaging in speculative analysis. The term theory itself refers to ideas that are subject to change and evolution, rather than fixed facts. Our knowledge stems from images captured by telescopes, sound waves, and radiation detected by radio telescopes, as well as data from neutrino and gravitational wave detectors. The JWST enables scientists to break down the oldest light in the universe into individual frequencies, providing an unprecedented level of detail. It can reveal which elements were present in galaxies billions of years ago, how much mass they contained, and the number of stars within them. However, the JWST's images do have some limitations. For instance, it struggles to distinguish between galaxies and black holes that emit similar levels of brightness due to gravitational lensing. As our understanding evolves, we consider different possibilities, often dismissing alternative explanations that may provide fresh perspectives. Recent discoveries from the JWST are shaking the foundations of modern physics, raising concerns among many researchers. The principles of physics today are still heavily influenced by Isaac Newton's work from the 17th century. For centuries, his laws of motion and gravity have formed the basis of our understanding of both the physical world and the universe. These laws work well under normal conditions on Earth, but in space, they needed to be extended, primarily through Albert Einstein's work in the 20th century. Einstein's special theory of relativity, published in 1905, revolutionized our view of reality, showing that the laws of physics are relative to the observer's motion. His general theory of relativity, published in 1915, further expanded on these ideas, predicting gravitational anomalies caused by the curvature of spacetime due to massive objects like stars or galaxies. While Einstein's theories have held up in many areas, he acknowledged their limitations and sought a unified theory to reconcile all of physics. Despite considerable progress, no scientist has yet succeeded in this goal. It's intriguing to consider where errors might lie. Michio Kaku, a prominent American astrophysicist, suggested that solving this problem could earn a Nobel Prize. There may be misinterpretations of anomalies, or perhaps the telescopes themselves are introducing errors. Dark matter and dark energy are leading candidates in the ongoing cosmological crisis. Current models propose that these mysterious entities account for around 95% of the universe. However, neither has been directly observed or conclusively proven to exist, leaving open the possibility that they may not exist at all, or that they could possess properties we don't yet understand. One hypothesis under investigation is that dark matter's properties could have evolved over time, potentially exhibiting forms of intelligence. Gravity, which is supposed to act through mass or spacetime curvature, has yet to be officially confirmed to behave exactly as predicted, despite the validation of Einstein's spacetime bending concepts in many experiments. A few possible exceptions in our understanding of key constants in cosmology might provide new insights into the universe and help explain certain anomalies. Without dark energy, for example, our interpretation of light shifts could be flawed, leading to inaccurate distance and age assessments of galaxies. Perhaps our assumptions about the conditions of the universe are wrong, or we may have misinterpreted the cosmic microwave background radiation. Another possibility is that the universe didn't originate from a single point, challenging the traditional Big Bang theory. Minor errors in the JWST's instruments or data processing can't be ruled out either. Scientists are fully aware that instrumentation, data analysis, and interpretation can always contain potential flaws. The continuous re-evaluation of cosmological models is a fundamental part of scientific progress. The ability to adjust and enhance our understanding based on new evidence is crucial. The observations from the JWST represent more than just technological advancement. They signify a pivotal moment in our quest to unlock the universe's secrets. As we process these new findings, it's important to consider the broader implications of these ongoing shifts in cosmological thinking. The process of refining theories to align with new discoveries is often driven by the desire to improve our understanding of the cosmos. While the revision of established theories can be unsettling, it also offers exciting opportunities for scientific advancement. Theoretical models in cosmology are designed to provide a framework for understanding the universe's origins, evolution, and development. However, as new data emerges, these models must be tested and, when necessary, revised. One major area of focus is dark matter and dark energy, two concepts central to modern cosmological models. Dark matter, an invisible form of matter that doesn't emit or absorb light, was proposed to explain discrepancies between the observed rotational speeds of galaxies and the mass predicted by visible matter alone. Similarly, dark energy was introduced to explain the observed acceleration in the expansion of the universe. Despite their importance, neither dark matter nor dark energy has been directly observed, and their true nature remains elusive. This has prompted scientists to explore alternative theories and potential explanations. The study of cosmic inflation is another intriguing area in cosmology. This theory proposes that the universe underwent a rapid expansion in its earliest moments, which helped shape the large-scale structure we observe today. While inflation theory has successfully explained many features of the universe, such as its homogeneity and flatness, it has also raised questions about the nature of the inflationary period itself. Observations that challenge established inflation models may lead to revisions in how we interpret the universe's early history. Finally, the search for extraterrestrial life remains a major driving force in space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up new possibilities for studying the conditions necessary for life. Advances in telescope technology, such as the JWST, allow scientists to analyze the atmospheres of these exoplanets for potential signs of life. The potential discovery of life beyond Earth has profound implications for our understanding of the universe and our place within it. In conclusion, the ongoing reassessment of cosmological theories in response to new data is a testament to the strength of the scientific method. The James Webb Space Telescope, along with other advanced observational tools, has provided remarkable insights into the universe, challenging long-held theories and prompting researchers to refine their understanding of the cosmos. This process of continuous inquiry and revision is essential for advancing our knowledge of the universe and addressing the fundamental questions that lie at the heart of cosmology. As we continue our exploration of the universe, we remain engaged in a quest for knowledge that not only aims to answer crucial questions but also inspires future generations to push the boundaries of human understanding. Carlos Plain, an educator at Durham School, expresses that his entire professional journey has been dedicated to advancing and empowering a distinct theory about the nature of the universe. Over the years, this theory has been scrutinized and adjusted, as new findings and discoveries challenge our understanding of the cosmos. Plain wholeheartedly embraces this continuous examination, as it is through such rigorous inquiry that we make strides in scientific advancement. The James Webb Space Telescope, JWST, has significantly disrupted established views in cosmology, long-held convictions that were once regarded as undeniable truths for over a century. Recent images from this telescope have revealed that previous assumptions in space science were mistaken. Initially designed to study the formation of the earliest stars in the universe, the telescope has unearthed problems in our previous models, suggesting that our understanding might need a complete overhaul. Yet, not all researchers are disheartened by these new revelations. Many in the field welcome these changes, recognizing that it has long been apparent that certain aspects of previous theories were flawed. The anomalies found in how the universe's expansion rate was measured should have raised flags for specialists years ago, but instead of addressing these concerns, many continued to cling to outdated paradigms. The cosmic microwave background, CMB, radiation, often considered the oldest light in the universe, was created roughly 380,000 years after the Big Bang. During this time, the universe had cooled sufficiently for electrons and protons to form stable hydrogen atoms, a phase referred to as reionization, which allowed light to travel freely. In 1964, American physicists Arnold Penzias and Robert Wilson made the accidental discovery of this radiation while working on a new radio receiver. They initially mistook the constant noise they detected for interference. However, this revelation would later become crucial evidence supporting the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize for their discovery, which turned out to be a major milestone in the history of space science.